Okay, so for the data set what we are doing, so that's way for the linear models of regression when we are calculating, we are doing in terms of the importing of mglearn and mglearn dot plots in terms of wave data set, and we are been extracting the weight value and the intercept value. So this has been shown very clearly where we are having here, that is the value in terms of the graph, which is a slope oriented intercept graph. That is a linear graph what you are getting, don't forget. And it is having a weight and b which has been shown here, and that is been operating here in order to extract the output what you want to extract, right? So that is the thing. So it is able to extract the output what we require, so it is able to generate that, right? So this is the thing what happens here. So we are been extracting the output of these things for the data set of your features which are to be generated in the using linear models. So here we have used a linear regression, okay, to predict the output for a single features whatever the thing we have, and we are having the x-axis of this one where you are having the prediction line which has been going towards the negative side, that is in terms of this is the thing what is being shown, okay, right? So this is the main thing with the linear regression. In the linear regression, most of the time this has been used in order to reduce the minimization of mean square error between the predicted and the true regression value. Okay, between the predicted value and also true regression value, we will try to reduce the minimum square error what has been there. This minimum square error is nothing but sum of the square difference between the prediction and the true values. Don't forget we have been doing this to predict this one. So after this, we are having the linear regression in terms of for the wave data set only, which we have seen yesterday, and we have calculated the coefficients also, right? And we have seen the results. Just we will be once again seeing that here, right? Yesterday we have run this program. Yesterday we have run this program, that is in terms of import mglearn from sklearn in terms of import regression and sklearn model selection, import train underscore test underscore split. So x comma y, that is mglearn dot dataset. We have loaded a boosted dataset here. Okay, not this, not boosted dataset. I think it is the right. Mglearn dataset, that is in terms of wave, that is n underscore samples is equal to 60, and we have asked for train and split operation, that is training and splitting operation which we want to do, and the random state we have taken here as a 42, and we ask it to run what is the linear coefficient and the intercept. So the linear coefficient value is 0.39 and minus 0.03 is the intercept. So you are going to get the same values what you have here, don't forget. See here, 0.399 and 0.3939, 0.3939 here also. So the linear regression for the wave data set, the weight value is same, and also the v value is minus 0.03. Here also we are getting minus 0.03 what we are having. Okay, so that is the thing. So this is been showing you out the information in terms of the data what we are going to get, which is your information of the intercept what we have been getting and the weight value what we are going to get. Okay, so that is the thing, right? So this makes to understand very clearly that we are been doing the operation of this information in terms of the intercept and the weight value to generate using the linear regression what we have been doing here. So that has been shown here, right? After that we are having about another one. We have seen the relevant in terms of the same thing only, no changeover, but in terms of name, which is called as a training score and test score. We have asked for the training score and test score to be generated. So that is being implemented once again with the continuation of this only. Right? So MG learn in terms of linear regression, and you have been having the coefficients, and next we are having about the training set score and the test set score. So it is having in terms of 67 and 66, very near. So it may cause some type of dispensaries in the mainly in the training and the testing. Why? Because you are having 67% and 66%. So as you are having the training is equivalent to that of testing, you may have some type of overfitting concept. Okay, so that is one type of problem you may get. To overcome this model of complexity problem, what we are having here, we go for having the operation of this one. That is called as, to overcome this one, we are going for an operation which is called as ridge regression. So there is another type of regression method, that is a algorithm which is there. So here we are using linear regression. Okay, now we are going to discuss that we are going to have now. Okay, in the dataset we are having about the linear regression, and now we are going to see the accuracy in proper way using ridge regression, right? So the main intention of ridge regression is one type of linear model only. It is also linear model only, don't forget. So it is consisting of coefficients of weights chosen and to predict the training data and also to do the regression in order to overcome the overfitting. Okay, what we are doing here is that we will be changing that in terms of this one as ridge. Okay, so just run the program. Okay, so if there is an error because you have changed only here it is being shown. Yes. Okay, ridge. Let's see. See, even in the ridge regression also it remains the same. So the data set is working, but the data set is working perfectly even you are doing the ridge regression. That it is having 67% of training, 66% of testing, and the weight and the quotient. So no problem in that data set. So now what I am doing is that now I am changing the data set. So I remain with the same program only. I don't change anything. A small minor changes, that is change in the data set and random state value. So what I'm going to do is that I want to clear mglearn dot load underscore extended underscore booster, and having a random state value as 0 only, and we will see what is the resultant, that is in terms of what we are doing is ridge regression only dot fit what we have, and we are going to have this one in terms of questions which are not required at all. Format ridge. Why? Because we are doing for ridge, no, RADG. Right, you can see in the ridge regression when it is implemented on the dataset, which is called Boston dataset. So when it is implemented on the Boston dataset, we have got in terms of the ridge regression where it is able to say that we are having 89 percentage of the training, and it is having the testing score of 75 percentage. So that is the thing. The training score is 89 percentage, and the testing score is in terms of having 75 percentage. So the training set score of which is lower than linear regression, but the test score is higher. So what this indicates is that your training score is 89 only. There you got 67, but your test is 66. Both are near, but here your training is more efficient. You have done a better training for your data, and it is been able to overcome the overfitting concept, and it is very much less complex model to have the data in terms of worst performance for the data training set, but it is better in generalization. Okay, it is a better operating in the generalization what it is being done. So that is the thing what it is being shown here in terms of your importance. So if the same thing you have been implementing in the ridge regression for the training data for the same data sets which are being there with some changes in the alpha value. So what we are going to do is that we'll be doing here in the ridge regression only without any alpha value we have done. We'll take a value alpha equal to 10. So in the previous case we are having 89 percentage and test score is 75. So now we'll run the program. Okay, there is a spelling mistake. Huh? Okay, alpha. See, in the previous case without alpha, the training value is 89, and in the training value with alpha equal to 10, it is having 0.79, 79 percentage, and the test score is 75 percentage there. Now the test score is 64 percentage. So what is the intention here is that there is a change in the dataset identification of training the data with the model to understand for the input with alpha value. With alpha value, when we have been operating in the model to extract the output to see how much it is able to train and how much it is able to extract the testing also, it is able to have some type of delay. That is not delay, it is having some type of reduction in the training score percentage with alpha equal to 10. Without any value, you are having a huge percentage 89. So what we are doing here is that to see whether it is having some better value or not, we will reduce some more, because you when you reduce to point 0.1 for example, and if you do the operation on this one, see here that now the training score is been going to 93 percentage, and the test score is going in terms of 77%. Okay, so that is the thing. So for the training without anything, that is without any value, when you run the program it is having 89, but when you are having with 10 it is 79, but when you are having with point 0.1 it is having 93. That is a training of score for a model with ridge regression inside for the input when you operate with the ridge regression in the model. In the model with ridge regression, if you are operating, then you are having the training score in that manner. In the same way, the testing also. Now, I'll combine all the programs now at a time. That is ridge regression without alpha. Without alpha is nothing but it is having a value of 1. It should be treated as 1. If you don't have the alpha value, it should be treated as 1. Otherwise, you have to give the alpha value as 0.1 or 10 or something. So these three with linear regression, all these three will be taken, and we will try to see what is the resultant output you are going to get. So we are not defined yet, sir. So that's why it is not able to say anything. Oh, input mg learn is also not there. We are not having linear coefficients here. Okay, you are having the linear coefficients now. So we'll write the linear coefficients. LR equal to linear regression dot fit dot fit x underscore train comma y underscore train scalar dot linear underscore model import linear regression. When we are typing, it will run the program automatically and it will do some changes. So you're getting something. No? See, you're getting. Previously, you got just only the things, but you're not able to know which color is for which one. But here we are able to define very clearly what is the color you are going to get for each and everything, right? So, what is the linear quotients and what are the values that you are going to get? So that I have been able to understand to you, right? So this is the thing what we have been giving. Now we are having another function which is called lasso function. So we are been using a function which is called as a lasso function. This lasso function will be working extension of this in order to identify the test score and how many features are being extracted, right? So when you run all these three models at a time, it will generate the outputs. You know? So these are the training and testing outputs, and these are your graphs what you are going to get, which we are showing to you. So now we are going to do the same thing here for your data set for the lasso function. So another we have seen the linear, we have seen the linear regression, ridge regression. Now we are going to see lasso function. Okay, lasso function which we are going to see to implement in order to extend the output, how much we are getting in terms of training and testing, and also in terms of the overall results with data for alpha values, right? So this is the thing. We are taking the value here alpha is equal to 10.1 and 1 only. Another one in terms of linear regression, and we are trying to extract the output what we want. Okay, we are trying to extract the output what we want. So that is the thing which we are able to get that. So that is being shown here very clearly. Okay, okay. Why it is showing? It is showing in terms of the information where we have been not able to show the resultant of things. That is strain and split problem. So that's why it is showing those all, right? So that's why it has been showing all these things. Okay. So we have not defined the X train and Y train. So which is nothing but the data sets. So I will be taking the same data set only. I will not changing the data set. Just I will take the data set and I will run the program. Undefined X and Y. See, you have to read the data set also. Otherwise, you'll be not getting no. So we'll take the data set of something which is required, and that will make to understand for that one. So it is an additional one import matplotlib which is not required. So we have been importing mglearn and we have been doing the operation in terms of train and test operation. In terms of split, we have uploaded okay. We have uploaded the linear model in terms of Lasso function, and we have been taking mglearn dataset, that is Booston dataset, and we are asking you to take the data in terms of training and testing speed. It has to do by itself. X train and X test, Y test, train and split in terms of X comma Y with random state equal to 0. And we are asking you to fit the data using the lasso function only. Lasso dot fit with X train and Y train. And we are asking you to print that lasso in terms of X train, Y train, and the coefficients. Let's see what the values you are going to get. So this is the values what you have been getting. That is the training set has 29 percentage, and the test set has a very less value. So to overcome this, let's in the lasso also we are having some type of parameters that we can implement. So that we are going to do now. That is lasso in terms of 001. That is lasso alpha equal to 0.01 max underscore bitter equal to 1. So as we are changing that in terms of lasso, no? Lasso in terms of 001. So when you are running this, now your percentage has been changed. As you're changing the alpha values of these things, and also in terms of the values of iterations, that is how much you are showing. So you have been getting a value here, 90 percentage of training score, and we are able to extract 33 features, and we are also able to have the test score 77. Right. So we'll go in depth in terms of 0.00 only, and we'll keep this in the same way, and we'll see how much it will be the resultant. Showing the value now in terms of 95% is training, but testing is only 64. But the features that are being extracted here is in terms of 94. It is able to extract the features in terms of 94. So you have changed one in terms of alpha. Without alpha, another alpha value is 0.01, another alpha value is 0.0001. So these are the three things. So at a time, if you want to see the output of